Hey everyone. What I want to do in this video is go through some of the key kinematics definitions, where kinematics is just how we describe the motion of objects. I see an object moving through some space, and I want to be able to mathematically quantify different aspects of that object's motion. Now, in other videos, we'll talk about dynamics, which has to do with explaining why different objects cause different kinds of motion, but that's going to be the topic of future videos. So let's start very simply in saying, what if I want to describe the position of some object in space? Okay? So let's say I have an object just sitting here, and I want to describe where that object is on the screen. Well, I could start from the center of the screen and say, well, this object is a certain distance to the left of the screen, of the center of the screen, and a certain distance down. Or I could start from the bottom left corner and say, well, this object is a certain distance to the right and a certain distance up. What I'm describing here are Cartesian coordinate systems that we can use to basically set up a grid from some arbitrary starting point and use those coordinates to figure out where is this object in this particular space. Now, there are other kinds of coordinate systems that we can use. Cartesians aren't the only kinds of coordinate systems, but this is usually the easiest one to get started with. So when we are choosing this kind of coordinate system, we have to make two choices. First, we have to choose where are we putting the origin of this coordinate system, or position 0, and we have to choose a positive direction. Okay? So for example, let's say I add a grid to this, and we can say, okay, I'm going to just call the original position of this object position 0, and I'm going to call up the positive direction. Okay, well then, let's say I wanted to be able to describe different kinds of motion. So for example, if I start this object moving, so it goes through some motion, and I want to be able to describe and quantify what's happening during that motion. Well, there's a couple of ways that we can do this. First off, we can draw what's called a motion diagram. And that's where at regular intervals of time, I'm going to put a dot where the object is located. So for example, every 1 second, I could put a dot at the object's location. So if I start the timer, that's at time 0 seconds, 1 second, 2 seconds, 3, 4, and 5. And we can look at the positioning of those dots to kind of get a sense of what's happening with this motion. Notice that as time goes on, these dots get further and further apart, which we might interpret as, oh, this object is starting to go faster and faster. The more those dots are spaced apart from each other, the faster the object is going. And while this does do an okay job at getting us some general pictures of what's happening with this motion, it does have some drawbacks. So for example, if these are the dots at 0 seconds, 1 second, 2 seconds, and so on, what if I wanted to know the position of the object at 1.5 seconds? Well, it's probably not going to be dead set in between these 2 points because, again, the speed is changing the entire time. So I might not have a super accurate way of measuring that. Now you might say, well, let's change our motion diagram. Instead of drawing the dots every 1 second, let's draw a dot every half second. So we can do that. So this is now drawing a dot every half second. And notice we're getting a lot more information, but what if I wanted to know the position at 1.7 seconds or 1.782 seconds, something arbitrarily accurate? Well, we could put in more and more dots, but as we put in more and more dots, this graph is going to get really, really busy, and it's going to be more and more difficult to measure what's actually happening with this motion. So instead of drawing a motion diagram, what we can do instead is graph the motion, make a position versus time graph, something that looks like this. So what we can do with this position versus time graph is track at different moments in time where is the position of the object. So if I start this motion going, then I can identify at any arbitrary time, let's say I want to know where the object is at 2 seconds. Cool, I can say at 2 seconds, the object is at position of, let's say, 1 meter. Okay? And that matches up with this motion diagram, but notice on this graph, I can find any arbitrarily accurate time, say 1.78 seconds, I could find where that is on the graph and read off what is the position at that particular time. So these graphs of motion, say a position versus time graph, it can code a lot of information if we know how to read these different kinds of graphs. So we're going to be seeing examples of that, and we can also look at this motion as an equation, a position as a function of time, where if you give me some time, some value for time that you're interested in, I can plug it into this equation, and when I sub that particular time in for our value t, we can evaluate what exactly is the position of the object. And again, we can do that to arbitrarily high precision. So it's going to be useful in different situations to be able to describe an object's motion using each of these methods: motion diagrams, using graphs of motions, and using equations. And we're going to look at examples of each of these as we continue on. But let's look at some more specific definitions for motion. So the first one that we're going to look at is the definition of displacement, an object's change in position. The way that we are going to denote this is with this Greek letter delta, so this little triangle symbol, followed by an X for position. And this delta symbol, this just means the change in whatever quantity comes next. So in this case, this is the change in position. And whenever we have a change in a quantity, we are always going to be evaluating that by looking at what is the final quantity minus the initial quantity. So in this case, since we're looking at delta X, change in position, that's going to be our final position minus our initial position. Now, if we're using standard SI metric units, which is what we are going to be assuming for most of this, those changes in position, well, those are going to be in meters. So the units for this displacement, the default assumption is that we're using meters for that change in position. A couple other important things. This displacement is a vector, so direction matters. If I have a positive displacement, cool, that means my position is changing in whatever I'm calling my positive direction, which in this case is upwards on the diagram. If I have a negative displacement, cool, that means my change in position was going downwards in whatever I call my negative direction. So displacement is a vector. And when we talk about more 3D cases where I could have an object kind of going through some weird motion, then the magnitude of the displacement would be the shortest straight line distance between the starting point and the ending point. And this is not necessarily going to be the same as the distance traveled. Unless it's going in an exactly straight line, never turning around, the displacement will not be the same as the distance traveled. So let's look at a couple of really quick examples for this. And let's say I want to look at this object's motion and track how does that object's motion change from the 2-second point to the 4-second point. So between 2 and 4 seconds, what is the displacement of the object? Well, at 2 seconds, our position is going to be just 1 meter. At 4 seconds, our position is going to be, looks like 4 meters. So if I want to calculate the change in position of the object during this interval from 2 seconds to 4 seconds, well, we do our final position of 4 meters minus initial position of 1 meter, and we just get 3 meters for a change in position. We get positive 3 meters because we are moving 3 meters in the positive direction. That was the change in position of this object during this particular motion. However, let's look at a more complicated example. So if I reset this graph, and let me change the graph around a little bit. Okay, so we have a different kind of motion. Let's just watch that motion for a second. Moves up, slows down, then moves back down and starts speeding up on the way back down. Let's do the same thing in identifying what is our displacement between the 2-second mark and the 4-second mark. So in this case, at the 2-second mark, our initial position, well, that looks like it's about 6 meters. And by the time we get to the 4-second mark, our final position is, well, it looks like we got 4 meters again. Okay. So in this case, when we do our change in position, well, our final position is 4 meters. Our initial position was 6 meters. So our change in position in this case is negative 2 meters. Our displacement between the 2-second interval and the 4-second interval over the course of that entire interval, our change in position overall is -2 meters. The object moved 2 meters in the negative x direction. But again, that's not the same as the distance traveled because it was still moving up a little bit and then backtracked. And we also have this effect of displacement is a vector quantity, so direction matters on there. Let's look at some other definitions. So if we look at the definition of velocity, velocity is the rate of change of position with respect to time. So let me reset this graph to what we had to begin with. Okay. So the rate of change of position with respect to time, that's what we're talking about with velocity. And our kind of definitional equation in this case is average velocity is my change in position, delta x, again, final position minus initial position, divided by my change in time. We have that delta symbol again, so this would just be your final time minus your initial time. Okay. Well, if we look at the units for this, my change in position is going to be in meters, divided by my change in time in seconds, so the units for this are going to be meters per second. And once again, there's a couple of important pieces of information that we have regarding this definition. First, velocity is a vector. Velocity is always going to be pointing in the direction that the object is moving in. And a little bit more generally, let's say I'm tracing the object of some motion. So let's say there is a fly that is kind of going around on some weird path. When I say that velocity is pointing in the direction that the object is moving at, if I'm tracing out the flight of this bee, then at any particular point, that object's velocity, that fly's velocity, is going to be going in a path tangent, in a direction tangent to whatever its trajectory is. So at this point, that would be the direction of the velocity at that particular moment in time. When it's over here, its velocity would be pointing in this direction, kind of so on and so forth. When it's over here, its velocity is going that way. So you can kind of map out what direction the velocity is going in at each of these specific moments in time. When we're talking about the speed of an object, speed is just the magnitude of velocity. So this fly that's going around, is it going along this path slowly? Well, then these velocity vectors wouldn't have a very large magnitude. If it's going along this motion really quickly, that would have a much higher magnitude for its velocity, a much higher speed. So again, velocity is a vector. Velocity cares about the direction of motion. Speed is just the magnitude of velocity. Speed does not care about the direction of motion. So how do we relate this to the motion on some of these diagrams? So if I play this motion, notice that for our motion diagram, it's related to the spacing of the dots on the motion diagram. The more those dots are greatly spaced apart, the greater the distance between those dots, the faster the object is moving. So notice that at the beginning of this motion, it's not moving very fast, so the dots are kind of close together. As the object moves faster and faster, those dots are going to get further and further apart. Now, let's say that we want to know what is the velocity, not the average velocity, but the velocity at a very, very specific instance in time. Well, if we want to find that instantaneous velocity, there's a couple of methods that we can use. If we know a little bit of calculus, and we have a function of position with respect to time, then we can use a derivative and take the derivative of position with respect to time to give us the velocity. Calculus and derivatives specifically are a tool that we can use to find how quantities change with respect to one another. So in this case, taking a derivative of position with respect to time tells us how is that position changing with time, which is exactly our definition of velocity. Now, if you haven't taken calculus, that's okay. We've got another method that we can also use. If I have a position versus time graph, the slope of that graph at a particular instant in time will tell us what that instantaneous velocity is. So for example, if I want to know what is the velocity right at this 2-second mark, I can look at the slope of the graph, and I can evaluate that slope by looking at that tangent line and evaluating the rise over the run. So at that point, we've got a particular slope, and we can measure what the velocity is at that particular moment in time. If I'm waiting till some other time, let's say at the 4-second mark, well, notice this slope is steeper. Okay? The steeper the slope, the faster the object is moving. And it also tells us about direction. If that slope is positive, cool. That means the object is moving in the positive direction. If that slope is negative, if it's aimed downwards, as you read that from left to right, then your object is moving in whatever you have called the negative direction. Let's look at a couple of cases of this with an actual motion sensor. So let's look at an example with the motion sensor. So this motion sensor is set up so that up is the positive direction. The motion sensor itself is position 0, and let's see what position versus time graph we get as we go through different kinds of motion. So if I start this, if I'm not moving, then there's no velocity and the slope should be approximately 0. If I slowly move this thing up, notice there's a small positive slope. If I move this up faster, well, that slope gets steeper. If I stop it again, well, then it levels out. If I move in the negative direction downwards, then that slope is going to be negative, and again, depending on how fast I'm moving that object, that's going to affect what the steepness of that slope is. So again, if I'm not moving, the slope is 0. If I'm moving slowly upwards, we've got a small positive slope if I'm moving in whatever we call the positive direction. The faster I'm moving, the steeper the slope, that's true up or down. And if that slope is negative, that just means the object was moving in whatever I'm calling the negative direction. And again, for this system, we said up was positive, down was negative. So we can match up some of those properties with actual data. So the next quantity that we want to talk about is acceleration. And acceleration is defined as the rate of change of velocity with respect to time. At what rate is my velocity changing at as time goes by? And from this definition, we get our average acceleration equation is just the change in velocity, delta v, which again, for this delta quantity, that change in a quantity, it's always final minus initial. So this would be final velocity minus initial velocity divided by the change in time. In terms of the units for this quantity, well, if I have a change in velocity, that's going to be, again, SI units are going to be meters per second, and we're dividing that change in velocity in meters per second by a change in time in seconds. So that would be meters per second over seconds, or more commonly called meters per second squared. Again, these aren't the only units that we could use. So for example, if I'm measuring my velocities in, let's say, miles per hour, I could write this as how many miles per hour is my speed changing by, or my velocity changing by per second. So that would be miles per hour per second. But again, the standard SI units that we're going to be using have this as meters per second, or meters per second squared. Again, some important points about this. Acceleration, again, is a vector. The direction matters. And this one is especially kind of important because it has to do with forces. And acceleration points in the direction in which the velocity is changing. Now we have to be very, very careful about this property and how to interpret it. So some rules that I generally recommend thinking about. If velocity and acceleration are in the same direction, then that object, its speed will increase. It will speed up. So for example, in this case that we have right here, if I start this motion, again, we're saying up is the positive direction, and in the equation, when I wrote this out, I gave this a positive acceleration. Okay, so that acceleration is positive, and notice that as it moves upwards, velocity is going up, the acceleration is up, and as that's going, the speed is increasing. Now let's say we change this and made this a negative acceleration. Okay, we're still starting at velocity 0, so my graph is kind of a little bit wonky in this case, but let's rewind this. In this case, I've got a negative acceleration. The acceleration on this diagram is pointing downwards. When I run that motion, notice the object is moving downwards. If it's moving downwards and the acceleration is downwards, if velocity and acceleration are in the same direction, that object's speed will increase. But that's not the only case that we can have. Because for instance, what if acceleration and velocity are in exactly opposite directions? So we can set this up in such a way that, let's say I'm going to have this negative acceleration, but I'm going to have a positive velocity. So something like that. Okay. So again, my initial velocity is going to be positive. It's going to be moving up to begin with, but the acceleration is in the opposite direction. And when we run this, well, if velocity and acceleration are in opposite directions during that portion of the motion, that object will slow down. If the velocity and the acceleration are in opposite directions, that object's speed will decrease. We can look at another case. Let's say I've got a positive acceleration, and we're going to start this off with a negative velocity, so something like this. Then at least during the first part of this motion, if I have a positive acceleration, so my acceleration is pointing up, but my starting velocity is going downwards, then notice during the first part of this motion, that object is slowing down. It's moving in the downwards direction, but acceleration is pointing in the opposite direction, so that's slowing down the motion of this object. So if velocity and acceleration are in the same direction, the speed will increase. If velocity and acceleration are in opposite directions, the speed will decrease. And we're not going to worry too much about two-dimensional motion right now, but just for future reference, if velocity and acceleration are perpendicular to each other, so at exactly 90 degrees to each other, then that object is going to start to turn. Okay? The velocity will turn in the direction of acceleration. And let's look at one or two extra cases of this. So let's say I have an object here, and let's say at a particular moment, the velocity is going in this direction, and the acceleration is going in this direction. Okay? This is not one of the cases that we have introduced yet. Okay? But let's see if we can build this out of a combination of some of these other cases. Well, from this diagram, velocity and acceleration, they're not going in exactly the opposite direction, but they're more opposite direction than the same direction. Okay? So this thing is going to first slow down. So we'll start slowing down. But it's also got that acceleration pulling a little bit to the side from the direction that the velocity is going in. So not only is it going to slow down, but that object's path is going to start to turn in the direction of acceleration. Okay? So from these three kind of base cases, we can build up other scenarios that are combinations and identify that this thing is both going to slow down because velocity and acceleration are kind of going more in opposite directions than the same direction, and that the direction of this velocity is going to turn in the direction of acceleration. So we have this equation of average acceleration, our change in velocity divided by the change in time. But if we want the instantaneous acceleration, so the acceleration at and around a particular moment in time, well, there's a couple of ways of identifying this. First, if we have the tools of calculus and know how to do derivatives, if we have velocity as a function of time, I can take a time derivative of that equation to determine the acceleration. Again, derivatives are all about looking at how quantities change with respect to each other. So if I take the derivative of velocity with respect to time, that by definition will tell me how is my velocity changing with time, and that's what we mean by acceleration. Another option is if I have a velocity versus time graph, again, not a position versus time graph, but a velocity versus time graph, the slope of that velocity versus time graph will tell me about acceleration. Same kind of thing. If the velocity versus time graph has a positive slope, excellent, you've got a positive acceleration, and the steeper the slope, the greater that acceleration. If you have a negative slope for your velocity versus time graph, well, then you have a negative acceleration for that object. And one last method, going back to these position versus time graphs, if we look at the curve of the position versus time graph, that will tell us something about acceleration. In this case, if I have a positive acceleration, this graph is going to have an upwards curve to it. Okay, it's not going to be just a straight line, it's going to have some curve to it. Even if my velocity starts as being negative, this graph, for the entirety of that motion, this has an upwards curve to it. It's sloped downwards right here, but that downward slope is getting smaller and smaller and eventually becoming a positive slope. So this entire time, we would have a positive acceleration because it's got this positive curve to it. On the other hand, if we have a negative acceleration, okay, if I have a negative acceleration, then the position versus time graph will have a downwards curve to it. Again, even though the position graph has a positive slope at this first part, as time goes on, the curve of that graph is going to start going downwards. So we know that this is going to have a negative value for the acceleration. So in summary, we talked about some of these definitions. Definitions for displacement, our change in position. Definitions for average velocity, how our position is changing with time. Definition for acceleration, how velocity is changing with time. And then we talked about some of this in graphical form and in calculus form. Again, if you haven't taken calculus, you can just use the graphical forms for this. How we relate position, velocity, and acceleration. So velocity would be the slope of a position versus time graph, or the derivative of position with respect to time. Or if I'm going from velocity to acceleration, the acceleration is the slope of the velocity versus time graph, or the derivative of velocity with respect to time. Going the other direction, we didn't really talk about this in this video, but if you look at the area under an acceleration versus time graph between two particular moments in time, the area under that graph will tell you your change in velocity. And we can also express this as an integral for, again, any of you who have taken calculus before. We can use an integral to define this as well. And if I know velocity versus time, then the area under that graph will get me my change in position. And lastly, we talked about these general properties that are really, really helpful to learn. What happens when velocity and acceleration are in the same direction? Your speed's going to increase. If velocity and acceleration are in opposite directions, then your speed is going to decrease. And if your acceleration is kind of to one side or the other of the velocity vector, so they're not perfectly aligned or perfectly anti-aligned, if the acceleration is going a bit sideways, that's going to cause the path of the object to turn in the direction of that acceleration. So just for some examples, again, here are a couple of examples of a few motion diagrams and trying to identify what is the direction of acceleration. So these are kind of listing from the particle always starts at 1 and then goes in a numerical sequence. So the object would start at 1, move to 2, move to 3, move to 4. Based on these motion diagrams, can we determine what the direction of acceleration is? And let's say a dog is running back and forth on field. If this is the dog's position versus time diagram, where the positive direction points east, try to describe how the dog is moving in each of these different sections. Is it moving quickly? Is it moving slowly? Is it moving east? Is it moving west? Things like that. And again, the solutions for this will be in the description. But that's what we'll call it for this video. If you have questions, as always, please let me know and throw those into the comments. Be kind to others as if you're answering other people's questions, and we'll see you in the next video.